Hello and welcome to another edition of 10 Buck Test Bench. And today we've got a short video on another flea market find, just to show you we can get some reasonable test equipment for very short money if you're willing to do a little elbow work, or put some elbow grease into it. We've picked up a Precision Apparatus Series E-200 signal generator. Now it's not like I'm hurting for signal generators. We have the little one back here that you've seen on the test bench in use before, sitting on top of the Heathkit frequency counter. And over here on the other side we have this Accurate Instruments unit that you've also seen me use to do alignments, and it works quite well. Both of these looked a lot worse than this E-200 did when I picked this up at the flea market. And this thing was, or is, very dirty. Its major issues so far appear to be it's missing the cap for the unused RF connector. Not a big deal. I think I've got one of those in the junk box. And it's missing the handle on the top. And as you can see, I paid $5 for this. Now these units sell for in excess of $150 on eBay. At least the E-200 C series does. The early E-200, I believe this has an 80 rectifier instead of a 5Y3. That's not a problem. That could be converted to solid state, or you could change the tube socket out to a regular octal socket and put a 5Y3 in here. No reason not to buy this because it's the earlier version. This is a professional unit, and it certainly will be a little more accurate and stable than that guy or this guy. Not that either one of those have a problem. You've seen me use them both, and in conjunction with a frequency counter they are just fine. You'll note all the original knobs are intact. Both of the indicator lines, lub lines for the dial are intact. There's some very minor corrosion on the screw heads. That's to be expected on something this age. The paint on the cabinet, we're missing some paint on the side. There's a little bit of rust. Same on the other side. Not bad at all things totaled up. The difference between this and the 200C, the 200C would have the indicator light over here, and there'd be a fuse located approximately here. And there's a difference in the tube complement, and there's probably a couple of other minor circuit modifications that have been made over the years. All in all, though, this is still a very nice signal generator. We're not going to bore you with the full restoration. We'll clean this thing up. Actually, we'll show you the insides of it real quick, and then I'll clean everything up off camera and show you where we ended up with it when we're done. However, for $5, a very nice score. So let me get this thing cleaned up, or get it opened up, and then I'll get it. We have the thing out of its cabinet, and as expected, there's plenty of mildew. As I've seen in other videos on these units, the people who built it left their initials all over the place, and this appears to be a date of 1946. Looks like 5/13. Well, that says 46, this says 48. Maybe 46 is the operator number, but it says 48 in here. Perhaps this was serviced in 48. Lots of paper capacitors that have to be changed. And down here on the bottom, we have our two so-called safety capacitors, which are actually RF bypass capacitors. And there's certainly nothing safe about leaving these old paper caps connected to ground from directly on the AC line. If these were to go to short, it would burn out these two chokes, or at least one of these two chokes probably, and could fill the whole inside of this thing with black smoke, as you saw in one of my previous videos on one of the other signal generators that I repaired. Both of these capacitors had gone to short and literally turned themselves into charcoal. The entire inside of the cabinet was black with soot. I had to clean everything out. So we'll get these paper capacitors out of here. Interestingly, they're Solar, which was a big name in capacitors back then. And you may have seen my video where I took you inside of my solar capacitor analyzer that I had on the bench at one time and sold off. And another paper cap here, another one down here on the oscillator unit. Note how nicely the oscillator is constructed. There's the central vacuum tube, reduce lead capacitance, made it a little easier to get up into the higher bands like 200 megahertz with these early vacuum tubes. Interestingly, there's no slugs to adjust the inductors for the low end of the frequency portion of the band on each scale. There is a trimmer cap for the high end, so we'll have to see how alignment goes on this. I expected an instrument of this class to have tuning slugs inside the inductors so that you could tune the low end of the band and then net it in at the high end. But at least each band has its own trimmer. The tube complement in this is interesting. I've printed out some schematics of various versions of this, and something's wrong with the PDF because it printed in green even though it was black and white on the screen. But that's okay, they're legible and we'll live with it. I have, let me back up a little bit here. We have 3 versions of this. We have this version, which is dated 3/11/1940, and in this version it's using an 80 rectifier 6SJ7 6C5. Now this unit has both of those tubes in it, but I have a 5Z4 rectifier in mine. This unit shows the 2 capacitors, safety capacitors across the line, which mine has. Here's the later version. Now this early one here is serial number 301 to 1300. This one is up from serial numbers 1301, beginning there and going up. Still has the same 2 safety capacitors using an 80 rectifier 6C5 6SJ7. This latter one from 9/20 of 1949 lists 5Y3/80, so you could find either tube in there, and it has the pinouts down here for, you know, what's using on the pin on the 80 rectifier, but it says 5Y3/80. They've gone to 4 capacitors on the RF bypass, so evidently these were found to be a little too leaky for modern receivers, too much RF leaking out the back door, so they added a couple more capacitors. Looks like they've also added, no, that's the single, yes, they've added another RF choke to this version. We have the 2 RF chokes that are here, and they've added one, it looks like, to the line cord of all things. So evidently they were having problems with the RF leaking out the back. So I'm going to test these tubes. We'll find out if the tubes are any good. If they're good, I'm going to leave them. If the rectifier turns out to be extremely weak, I'll change it out for a 5Y3. But typically, the rectifiers last a very, very long time. We'll test the other 2 tubes, the RF oscillator and the audio oscillator. What else? Oh, the filter capacitor, of course, has to go. It's been leaking wax all over the place inside. I've been finding lumps of wax. So we'll get the filters changed out. We'll get these paper caps changed out so that we don't have anything damaged from a paper cap going dead short. Clean out some of the mildew that's growing on the wires in here, and it's not horrible. It doesn't look like it's been extremely wet. Surprisingly, the dial lamp still works, so either that's been replaced or it doesn't have a lot of hours on it. At any rate, excuse me. No, it's still there. I had a little coughing jag. I ate an English muffin and the crumbs are stuck in my throat. Anyway, we're going to get this thing cleaned up. We'll get the capacitors changed. Change any weak or bad tubes we find, and again, I don't suspect that I'll have to change tubes. You never know. But 90% of the time on this old equipment, I find the tubes are fine. It's just the capacitors that have to go. We'll check the alignment. If it needs it, we'll try tweaking the alignment in and show you how we made out. Okay, through the magic of YouTube, we have completely recapped this unit. Now let's take a look at what came out of here. Here's the pile of components that came out. Here's the line plug that was on it with a very rotten, cracked cord. This is not original. The original would have been a fused plug. It would have had a fuse on both legs as shown in the schematic, and I didn't have any of that style. And I prefer to change this equipment over to a grounded 3-prong plug anyway. I know it's not original, but it's far safer. It works better for noise suppression. Anybody who doesn't like that in the future can merely remove this and put back an old 2-wire plug if they liked. But at any rate, that was well past its sell-by date. All of the capacitors in here, interestingly, all of the paper caps and in fact the electrolytic are Solars. And Solar was a very well-known capacitor company in its day. However, with the everything was Solar with the exception of this one Aerovox. Every capacitor in here was bad, and when I say bad, these are 400 volt rated caps. They were leaking seriously at the 25 volt level. They had to come out. And it's interesting to note that, move this thing around here and come back up on the zoom. These 3 little electrolytics replace that guy. And that guy was mounted with 2 straps on the existing screw holes that are here. I merely mounted a terminal strip there and put a strain relief down here. That's the original filter cap replaced by those. I've added my name to the provenance inside of this. Throughout this chassis we've got initials and dates, 1946, 1948. There's an ME over here, whoever he was. There's a letter A on top of the box covering the attenuator. There was one other set of initials. I got the ME throughout this thing. Oh, down here in the bottom there's a CC underneath on the bottom. So many people, probably these were guys that built it, aligned it, did the mechanical assembly, whatever. People took pride in their work back then. We have added a line fuse here to replace what would have been in the power cord. And on the bottom, I know it's not original, but I've added a strain relief so that if the plug gets yanked and it's grommet, normally they just had a knot, but the twisting, constant twisting back and forth breaks connections off. And I also put a terminal strip here so that if the strain relief fails, the cord won't rip apart these 2 inductors. It'll pull apart this terminal strip. We've tried as much as possible to keep it original, but we have to make some upgrades for safety. Its construction is obviously that of a... one thing before I forget to mention this. This enclosure for the attenuator, this is where this capacitor is located, is under this cover. Super critical that that one gets changed, that you don't ignore it because it's tough to get at. If we take a look at the schematic, that's a newer schematic. Take a look at the schematic here. Directly off the plate of the oscillator is this resistor R2, which is what the value of R2 here. R2, this is a 4K resistor. That's the only thing between you and the B plus is this capacitor and this 4K ohm resistor. If this pot is turned all the way to one end and this one's turned all the way to the same end, all this potential comes right out of the RF port if this capacitor goes bad. Do not neglect changing that one. It's not obvious it's there. It's a little bit of a pain to get to, but you've got to get that one changed out or you're exposing yourself to the B plus voltage at the RF connection in the front, as well as any equipment you're working on. We'll cover more on these schematics in just a minute. Very obvious that this is a commercial unit meant for the professional And unlike these smaller units like the signal generator that's right there, or the other one that I had on the bench, you've seen my previous videos, some of those signal generators. Look at this power transformer. That's almost 2 1/4, maybe 2 3/8 of an inch tall. That transformer is probably good for a couple of 100 watts easily. Whereas those other signal generators have a little small power transformer that's about 1.5 inch cube, maybe 1 3/4 inch cube. This piece of equipment was meant to be turned on, warmed up, and left on. Probably this thing ran 24/7. They would turn it on and simply let it run. And with this extra capacity, the power transformer would be loafing. It wouldn't have a large temperature rise. It would last for years, as is evidenced. This is 1946, 48 equipment. Still going strong, other than the capacitors. Oh, interestingly, all of the carbon comp resistors in here were good as well. They were well within tolerance. I was amazed. I've never seen resistors of this vintage, of this style, that were all of them. You know, usually you find like 20% of them have drifted to 2 or 3 times their normal value. They were all within tolerance, so I left them in place. So that power transformer would run 24/7, wouldn't even breathe hard under this load. This thing was just designed to run and run and run. And I believe these tubes are original. Now, all of the schematics show either 80 5Y3 or 5Y3 rectifiers. This is a 5W4. I believe this is factory. I believe this is the correct tube for this unit because, let me get my RCA tube manual. Okay, I looked up the specs on the 5W4 and the 5Y3. This has a 25 ohm plate impedance. The 5Y3 has a 50 ohm plate impedance, which means the voltage drop on this under load would have been slightly less and would have probably given them better regulation. For the trouble is, this tube became obsolete in the 50s, and the 5Y3 rectifier lived on for many, many years, so they probably switched over to the 5Y3. This is an early unit, shortly after they got rid of the 80 rectifier. So I believe that's original, and they're all Kenrad tubes. They're all the same brand, and it seems like everything in here, whether it's capacitors, resistors, all are the same brand. So I have to believe, or I'd like to believe, those are the original tubes, still soldiering on after almost 70 years at this point. Another interesting note that shows you this is a commercial unit. I hope we can see this. For many years, I wondered why they didn't put a flexible lead on tuning capacitors and only relied upon the sliding contacts. Well, sure enough, this capacitor, I don't know if you can see it, has a flexible lead in here that wraps around the shaft and is bonded to the frame and bonded to the rotor. That way, there is absolutely no dropout and no noise. You're not going to get dirty connections or a scratchy or jumpy tuning capacitor. I keep calling them condensers because that's what they were called back in the day. So this is not going to have that issue. Now, the problem with doing that, when you start getting up into UHF, you get inductances and you get issues. But back in the day when this was made, this is a 44 megahertz top band unit. Excuse me, on its fundamental. No, it's not even on its fundamental. I'm lying to you. It's 22 megahertz fundamental, 44 on the second harmonic. So that was considered UHF back then. So this would have been perfectly acceptable at those frequencies and would have worked out just fine. Let's take a quick look at some of the schematics here, if we may. And we'll go through some of these units. There's been some interesting design changes. Oh, and I should mention here also, this is an E-200. And it's virtually identical on the face to this E-200C that you see. It has the same number of bands, 1, 2, 3, 4, 5, 6 bands. Virtually identical, except the pilot light's been moved from the central location to here, and the fuse is gone from the line cord to the front panel. They also call this one an E-200C. But there's a big difference here. We still have the 5Y3 rectifier, but we have a 6U8, and let's see, what's the other tube that they were using? We'll show you in just a second on the schematic, but just while we're looking at this. 6AU6, so they have a 7-pin 6AU6 on the side of the turret instead of the tube mounted on the back. And up here we have the 6U8 for the audio oscillator. It's a dual tube, triode, pentode. Triode, pentode, 1, 2, 3, 4, 5, yeah. And that's mounted here. The filter capacitor is now mounted here. That central divider that's on mine is not here anymore. Now, what's interesting is this shows 7 bands, 1, 2, 3, 4, 5, 6, and 7. And there's 1, 2, 3, 4, 5, 6, and 7 pattern capacitors on the back. Yet the schematic that comes with this clearly shows that this unit had 8 frequency ranges and 8 switch positions. So they were constantly changing this unit, upgrading it as the years went by, and obviously weren't updating their photographs fast enough, because this is showing 7 positions. This one is showing 8 positions in the same. These two are from the same manual, interestingly. Some other design changes that they made over the years. Let's see here. Let's get them in sequence. 527, 58. Okay. Excuse the fast motion. I'm sure that's getting blurry in the camera here. Trying to get through this without making this video hours long. This is a schematic from 5/8 of 1940, May 8, 1940. The B plus for the oscillator is brought, or excuse me, not the B plus, the screen voltage for the oscillator is brought in through the tank circuit. We come from the B plus supply, we run through R7, we run through the tanks, then we run to the screen. And this has a grounded grid on the oscillator. We have our line cord with our fuses, dual fuses, and we have our RF chokes and bypass capacitors on the primary. Now let's jump forward just a few months, or excuse me, not a few months, 2 weeks. Jump forward 2 weeks to this schematic. This is 5/27 of 1940, just a couple of weeks later. This schematic shows the screen voltage coming directly through R7 to the screen. The cathode is no longer grounded. I say grounded grid earlier. I'm talking before I'm thinking here. Grounded cathode. If I said grid, I meant cathode. I'm sorry. The cathode now is grounded through the tank circuit. Completely different configuration. They've gotten rid of having B plus on the coil, so it's now you can go in here and handle the coils without getting worried about getting seriously bit. So that change happened in 2 weeks, between May 8th of 1940 and May 27 of 1940. We went to running the B plus directly to the screen through R7. The output attenuator remains identical, as it does through all models so far that I've seen. And both of these maintain the oscillator. The audio oscillator gets its phase inversion through a transformer. It's how they generate the phase inversion for the 400 hertz. Now we jump to 9/15 of 1949. In 1949, we went from strictly an 80 rectifier. Now they're mentioning, so that's several years, that's 9 years later, they're mentioning 5Y3 or 80 as the rectifier. They don't put any pin numbers down, so either tube could fit into this schematic. We've added 2 RF chokes here and 2 line capacitors here, so they're going through a double filter on the line. Oh, I should mention, this line cord I used turns out to be shielded, so any RF leakage there is completely shielded on my line cord. That was not by choice, that was by accident when I chose the cord. All right, we have a double set of RF chokes and a double set of bypass capacitors versus the single chokes and the single capacitors of the earlier version from 9 years earlier. Now let's jump to 12/7 of 1957, quite a few years later. Gone are the 6C5 and the 6SJ7, and in their place is a 6U8 with a capacitive network phase shift. We've gotten rid of the transformer. This is far cheaper to use 3 capacitors than it is to have a custom transformer made. And a 6AU6 in the oscillator. The attenuator on the output is virtually identical. Same resistor, same capacitor, same 2 potentiometers, same resistor here, 4,000 ohm resistor for the low RF output. Oh, and I said all of the resistors were fine in my unit. They were not. I lied. This R101, somebody obviously had pumped voltage into this attenuator network. Unfortunately, they didn't hurt the potentiometers. They're wire wound, but they cooked this resistor. So while I was changing this resistor inside the capacitor inside the attenuator, I noticed that this resistor was charcoaled and changed it. And the only way I noticed that was charcoaled was because I changed this over from those round microphone style connectors to more modern BNC connectors here. And I've maintained, the original had a cap on the microphone connectors for the unused jack to seal up any RF leakage. So I maintain that type of physical arrangement, and I used a BNC cord on the same original chain that was here. I just added a little length. This does not harm the unit in any way. The diameter of the hole for the BNC connector is identical to the hole needed for those round microphone connectors with the button in the middle of them. It's just such a pain in the ass to make cables up for those. It's much more convenient to use BNC connectors. However, the reason I mention all of that nonsense at all is on the back of those microphone connectors, there's like a barrel on the back of them with a hole, and that 4K ohm resistor that's here in the schematic, right here in the schematic, that's inside of the barrel of that microphone style connector, and you can't even tell it's in there. All you can see is the wire going into the back of the hole, and you'd never know there was a resistor in there unless you looked at the schematic or took apart that connector. So I'm sorry if I'm jumping around a little bit here. I'm trying to get all of those gotchas out of the way. I try not to make my videos about, look at me changing capacitors, look at me changing resistors. I try to cover some of the history of this stuff, and I try to cover the gotchas if you're going to work on one of these. I think I mentioned I paid $5 for this. I paid $5 for this at the flea market, and that's really about all it was worth by present day numbers. The same thing goes for that signal generator over there, any of the Heathkit signal generators, any of the ICO signal generators. I see those things selling, or people asking $40, $50, $60, $70 for those signal generators. Ludicrous, people. Do not pay those prices for those signal generators. Those are $5 and $10 signal generators. Period. End of subject. Unless you're a collector and you're collecting that last piece of Heathkit or that last piece of ICO gear for your collection, don't buy them at those prices from anyone, even if they're restored. Unless you're a collector, $5 and $10 is all you want to pay for these. Why? Even this unit, which has a lot of band spread on it, they're not precision. They were considered precision in their day. They claim 1% accuracy on these. Yeah, maybe on one that's been tweaked at the factory and played with forever. They're not that accurate. I always use these in conjunction with a frequency counter, and we'll show you the accuracy of this in a minute. I'm trying to keep the video short. You can buy brand new digitally synthesized signal generators for $30 and $40 and $50, the prices they're getting for that old ICO stuff, that have a frequency display on them. You punch in the frequency, you're on that frequency. You're not guessing like you are with these. These you have to use a frequency counter with them. Now, if you get this for $5 and you get the frequency counter for $10, you got $15 invested. Great. Wonderful to have this old gear. It's fun to use. The beauty of this is you're learning electronics as you restore it. You get to do some troubleshooting, you get to do some repair work, and you've invested $5. If you screw up, big deal. You go back, you learn something. Don't pay $30, $40, $50, $60 for Heathkit signal generators, ICO signal generators, whatever the name on that is. I can't remember the name on that thing. And the other one I've got here, let me grab it real quick. Oh, what did I do with it? I don't even know where I stuck this stupid thing. Oh, here it is. This guy. I'm not saying it's a bad signal generator. It works fine. And this piece is actually, I think, a semi-professional unit. It's got all the important frequencies marked on it. It's got a built-in signal tracer. There's a speaker audio amplifier built into this. Not a bad piece in its day, probably. But again, you're guessing at the frequencies on these. They're close. They were close enough in the day for working on old AM radio receivers. But today we want a little more accuracy. So please, resist the urge. Again, unless you're a collector, don't go out spending stupid money on this stuff. This is for educational purposes, for the enjoyment of restoration. If you're seriously going to spend $30, $50, $60 on a signal generator, buy something modern that's on frequency if you've got that kind of money. This is for the young players that want to buy something cheap, do some experimenting, have a signal generator around. Wonderful stuff to play with. Don't throw your money away. Okay, one last thing on the schematics, and then we'll get to showing you how well this unit works or doesn't work. The original circuitry up through the early 40s, actually this is 49, we have a single tuning capacitor right here for setting the frequency. And up here, this is our single tuning capacitor, which this unit has. And again, this unit goes up to 22 megahertz fundamental, 44 megahertz with the second harmonic. And these are all very, very rich in harmonics. In fact, this is so rich in harmonics that my Heathkit frequency counter doesn't even read with this. There's just too many harmonics mixed in, and it confuses the daylights out of the Heathkit. I've had to go over here to this data precision unit that has an adjustable trigger level so that I can pick where in the sine wave the triggering's happening, and that will accurately read the frequencies out of this signal generator. But the Heathkit that's sitting over there right underneath that signal generator won't deal with it because it's simply too rich in harmonics. That thing doesn't know what to make of the signal coming out of it. The harmonics can be useful, don't get me wrong. This latter version from 1957, however, is advertised as going up to 440 megahertz, and their claim to fame with this unit was electronic band spread. Well, what they've done is they've split the tuning capacitor into two pieces. They're both on a common shaft. They both tune at the same time. Now, this is a lousy reproduction scanned in by somebody. Unfortunately, the scanner they used was probably a printer scanner, early one, you know, like a copy machine scanner, and it just isn't very clear. It's not sharp. We have several plates on the capacitor here and what appear to be two plates on the capacitor here, both on a common shaft, both tuned together. On the lower frequency bands, on the lowest frequency band, or excuse me, we're combining two capacitors. When you get up to the higher frequencies, the switch goes over to a single section, now that two-plate section of the capacitor for the upper frequency segment. That's where their band spread comes from, is now they're using a very small capacitor. And the ranges, their fundamental was 55, the highest band, a band H on this schematic, is 55 to 100 megahertz fundamental. Then they have what they call the H2 band that goes from 110 to 220 megahertz. That would have been the second harmonic of the 55 to 100. The H4 band is 220 to 440 megahertz, which is the fourth harmonic of the 55 to 100 and 10 or 100, yeah, 110 megahertz fundamental. So they're using frequency doubling and frequency quadrupling for the two higher ranges. And it's funny, they say because of the fine or the excellent construction of this unit and the components used, the unit is extremely stable and accurate even using the fourth harmonic. Well, brother, let me tell you, if you're trying to dial in 445 megahertz on the fourth harmonic with the tuning ratio of these capacitors, you're going to be ripping your hair out. Probably great at the 100 and 110 megahertz fundamental, but it's going to be tricky trying to tune this thing in with their electronic band spread. And they're claiming 1%. I just find that hard to believe. Okay, let me put this thing back together, and we'll hook it up to the frequency counter and see how it performs. As I put this thing together, I'm going to touch on something that I always touch on. I'm going to keep harping on this until people pay attention. When you put screws back in, these self-tapping style screws, turn them backwards. That one you're not going to hear for some reason. Let me do it with this one. Hear that click as I turn the screw backwards? That means it just fell into its original threads. Then it'll spin in with no torque needed whatsoever. Don't just wind these things in. You're going to rip the material out, cut a new thread, and after 2 or 3 insertions, the screw's not going to hold anymore. There won't be any more sheet metal left. Please preserve this equipment. Turn the screw backwards until you hear the original thread fall in, then spin it in. If it takes torque to put it in, something is wrong. Oh, and if anyone knows a source, US-made source of these round button, or not button head, these round head Phillips screws, self-tapping, number 6. If anyone knows of a source in the US, drop me a note down there in the doobly-doo down below so that I can replace these. I don't want to buy cheap offshore screws. These are those self-threading, self-cutting screws with the round Phillips head. These are rusty. I'd like to replace them, but I haven't been able to find an exact source of these. I'm sure somebody out there knows where to buy these. Okay, the unit's together, on, warming up, and while it's warming up, we're going to give you a couple more gotchas. Now, you may have seen this in the beginning of the video. I don't know how close attention you paid. We've squirted a little bit of paint on this. We took the serial number tag off, squirted a little paint on. We were fortunate with this unit. It appears to have all the original hardware. To get this out of the case, you remove the 2 screws on the back here. And the screws all around the face panel here. Let's see, there's 3, 6, 7, 8, 9, 10, 11, 12 screws. 12 screws in the front, 2 screws on the back. On the top of this unit, it has one of these little snap-in plugs. What that's there for, I don't know. There's nothing underneath there. This is not, you don't have to remove this to take the front or remove this from the cabinet. It serves no purpose that I can see whatsoever, unless this was just a stock cabinet that they had and, you know, they filled the plug. I don't know. The handle's missing. I took the D-ring sections off. That way we can stack it. But a little bit of flat black paint over the wrinkle finish, and it cleaned right up. It really is not a bad looking piece of equipment at this point in time. Alright, let's see how this thing works. We'll grab a cord here, plug this into the RF high, and I'm going to plug the scope in as well. Oh, I know I've got another cable here somewhere. And I forgot to close the door. My sister's got the TV on. We're on band A, which covers 95 to 250 kilohertz. I've set it on 150 kilohertz. And we have 150.95 or 9 kilohertz, somewhere in that region. And as we can see up here on the scope, the signal's not all that bad, and the Heathkit would read this one just fine. Let's go to the next. Well, actually, let's see what the band ends look like, band edges. At 250 kilohertz, we have 250.09. At 95 kilohertz, let's get it as math. Yep, not too bad. 95.2 kilohertz, not horrible. Band B will start at the center of the band. That's 350 kilohertz. Whoops, it's reading. We're reading double here. Let's see if we can get that to read. There we go. Whoops. By setting the trigger level correctly. We got 351.99, 352 kilohertz. So we're off about 2 kilohertz. Not horrible. We'll go to the 600 end, 600.7. Let's go down to the bottom, 220 kilohertz. And I got to reset the trigger level. 221. So we're off about 1 kilohertz on that end. Band C, which center of the band about 900 kilohertz, and again we'll have to reset the. There we go. And the reason I'm resetting the trigger level all the time to read correctly is, let me get this up on the scope displayed here. Okay. You can see the harmonics. Let's see, spread it out a little bit more. As you can see, we have a harmonic right here, and if I don't set the trigger level down here at the lower end at the fundamental, that unit gets fooled. It has no idea, and the Heathkit can't even deal with this at all. The Heathkit just jumps around random numbers on this signal. But the fact that I can set the trigger level down here on this frequency counter allows me to read the frequency accurately on this unit. Alright, so 900, 900, 902. We're off 2 kilohertz there. This should be 550 kilohertz here. And we're reading double. There we go. There's the fundamental 549.8. Pretty darn close to 550. In the real world, you could use this unit to set up one of those old antique AM radios just fine without the frequency counter. It's close enough to set those up. They don't have the frequency resolution that this signal generator does. The signal generator is far more accurate than the dial scale on most of those early radios were. Unless you're using a professional or a ham receiver. You know, the standard cathedral radio or the standard, console radio of the day of the 40s and 50s, even into the 60s, this is perfectly adequate. Now, this is set on 1700. We've got 17, 2, so we're off 2 kilohertz on 1.7 megahertz. This would be 1.7 megahertz. This only reads in kilohertz. Let's see, band D. Band D. Right now that should be 2.5 megahertz, 2.497. Pretty close. Close enough for setting up any of those early receivers. There it is. It dialed right in. Let's go to the high end, or excuse me, the low end, which would be 1.6 megahertz, and we'll try to get that as close as we can on the scale. 1.604, so we're a few hundred hertz off there. Big deal. And we'll go to the high end, which is 5 megahertz. 4 point, close enough to 5 megahertz for the girls I go out with. Band E. Let's see here. Where are we? Band E should be, okay, we'll start here at 3.8 megahertz on one end. I'm trying to rush through this so the video isn't too long. So there's 3.803 megahertz. Not bad. Not bad at all, to be honest. Okay, a little interruption there. I had this video running on a separate memory card from my normal one, and that card was nearly filled when I started this video, but I wanted to keep this video separate from 3 others that I've got partially completed on the other memory card. I've just been going crazy trying to complete projects, and that card ran out of memory, so we're going to finish up on this one. Okay, so 10 megahertz was real close. This is almost over. The pain's almost done, guys. And now we're on the highest band, and let's see, that should be 25 megahertz. Is that right? Am I looking? No, that's F2. F should be 12, yeah, 12 megahertz. The other band runs on harmonics. That'd be F2 band. So there's 12 megahertz. That's close enough to 12 megahertz, to be honest. The second harmonic of that, of course, would be 24. I don't know if I'll be able to pick it up on this. No, you'll have to mentally do that because it's probably fairly clean, so it's not showing a second harmonic on the frequency counter. I can't show you that on the scope because the scope only goes to 10 megahertz and it's out of bandwidth. So maybe I can resolve it. Oh yeah, I can actually. It's a very clean sine wave. It's down considerably in level because it's so outside of the scope's bandwidth that you can see the signal level has just shrunk to nothing. Of course, the output of the generator has likely dropped as well, but I know there's more voltage in this coming out of the unit. It's just we've hit the edge of the bandwidth of the scope, but it's a very clean sine wave. I hope you can see that. It's actually pretty decent, or at least it looks decent on that scope. It may be horrible. Oh gosh. Okay. So 12 megahertz, let's get this over with, Vern. Let's stop dilly-dallying. There's 22 megahertz. And come on, where's the trigger? Yeah, find the trigger point. There we go. 22. We're about 800 kilohertz off on 22 megahertz. That's not surprising. Any error at this frequency is going to be multiplied greatly. And this is supposed to be 7.5. So one end of the band is actually, there it is. That's actually 7.5 megahertz. It's actually pretty good on that low end of the band. I can't do anything about this because none of these generators have, they have a trimmer capacitor for the high end. I could adjust the high end, but then the low end would be off because there's no slug in the coils to adjust the low end response or the low end frequency resonance. So a resonant point of the low end. Blech. Easy for me to say. There you have it. I like this generator well enough that I am going to keep my eye open for some of the newer versions of it. I'd like to have several iterations of this just because now I've got the bug to collect them. Now that I've seen the different versions in the manuals, I'm curious to see how they stack up against one another. But again, I'm not going to go out and spend $30, $40, $50 for one of these. If I find another one for $5 or $10, I will buy it. and I'll give you a brief video of the comparison between the two. But if I'm going to spend $30, $50, $60 for a signal generator, it's going to be something solid state, something accurate. It's just ludicrous to spend that kind of money on this older gear. Again, unless you're a collector. So remember, guys, this is the $10 test bench. Try to keep it within $10. You know, 15 is probably reasonable, but now you're starting to figure in, I paid $5 for this. I've probably got $10 in capacitors in it right now. So I've got $15 into this unit plus my labor. And believe me, this video, while however long it ends up being, I don't know because I haven't looked at the timeline. I haven't started editing yet. I've got 3 days work into this video just to put this together, digging up the information, finding the parts, working on the unit evenings. I've got probably 30 hours in this. And by the time I get through editing, I'll have another couple of hours. It's whatever your time is worth. It's fun to collect. You're learning something while you're working on it. That's the way I look at buying this stuff. But again, don't pay $50 for it. Buy something usable. If you're going to spend $50, buy something that works off the, right out of the box. I'm the Radio Mechanic. This has been another edition of $10 Test Bench. Hope I didn't bore the ears off of you. Hope I didn't sound too rushed. I'm trying to keep these short. See ya. Oh, and subscribe, damn it.